Hello, everyone. Give me a thumbs up if you can hear me. We are online again for another session of Community Conversations. We're here for Technomatics Virtual User Group. Today's topic is Perl chain optimization with a genetic algorithm. So, as I mentioned, Mr. Stefan Bongso is back with us. He is a freelance simulation expert, as many of you know, and he's been in this simulation space since the 1990s. He has 5 books on plant simulation and is one of the leading contributors to our Siemens PLM community and one of our community catalysts. So he's an expert. We appreciate him and his expertise for us here. Today's session, the agenda, Stefan is going to go through a basic scenario, show the GA wizard configuration, do a fitness function, and look at optimization and results. So as most of you know, we are live always when we do these sessions. We're absolutely live. So everyone is on mute with camera off right now, but we will have a live Q&A after the session, the presentation portion completes. So during the presentation, feel free to put your questions in the chat, and I'll be monitoring that. And then afterwards, you can definitely come off of mute, just raise your hand, I'll unmute you. You can ask questions using your voice. Of course, that you can also use the chat, but we'd love to hear your voice and we appreciate the questions. So that is all for my introduction. We are recording today, and Stefan, when you are ready, feel free to steal the screen.
Okay, our today's topic is about optimization. It's for me frequently asked questions, okay, how we can use plant simulation for optimization. And many optimizations is we look for the bottlenecks in a system, and then we increase the capacity in this bottleneck, and then we get a better output. Another kind of optimization is to change the order of inside of a sequence to increase the throughput in this way. And you can only make such optimizations if the order inside a sequence matters somehow. And there are two big topics here. One is setup times. If you have setup times that are different between if you set up from A to B, maybe you have only to change some settings in the machine and it's done within some minutes. And if you make a setup between A and C, maybe you have to change all the cribbers and clamping devices, and this may take an hour. And so you can try to find a sequence with a minimum on setup time. Another kind of optimization is if the parts don't have the same technological steps. If you have different work plans, then maybe you can make in parallel. If you have one bottleneck or in your production, maybe you can do some in parallel. And such a kind of production I want to show you today, and how to optimize the sequence using the genetic algorithm in plant simulation. Genetic algorithm is only available for the professional license. If you have another license type, then you cannot follow the day. Okay, so first we need one basic scenario, and I've prepared one, and I want to create this first. Okay, I want to produce 4 different parts, and today I start with work plans. So I take a table, I name it work plans. And I need the row index and column index. Row index in the row index, I have my products, and in the first column I have the work plan. I want to have A, B, C, D, 4 different products, and work plan. This should be a table. So I format this column as a table. I click apply, and then you need to format this subtables. I want to have the column index. In the first column, I want to have the machine. As object. In the second column, I want to have the proc time, the processing time as time. Okay. And now I can create work plans. My product E should be processed on M1, M3, M4, and at the end it goes to train, and proc time is 1 minute, 3 minutes, and 1 minute. So it colors this red because I don't have this objects now in my frame, and so it changed if the objects are existing later. Okay, this I can take as a base for create the other work plans. I can copy this with Ctrl+C and place it here as a blueprint for the work plan of B. It should start with M1. Then I insert a row here. It should continue with M2, and it takes 10 minutes. Then comes M3, maybe 2 minutes. M4 with 1 minute, and then train. Okay. Make M2 here a little bit longer than that we have here clearly a bottleneck in M2. Then C. M1, M3, each 5 minutes. And no M4. I delete this row. I have only 2 steps. And a work plan, a work plan for D. M1, 2 minutes. Then M2, 2 minutes. And M4, 3 minutes. And then train. So we have for each part, we have a different work plan, a different order of tasks. Very interesting is if you come back to a station, then it becomes more complex. And now I can create my basic frame here. I need a source. And I need 4 stations. I activate names for the station, 3D properties, and then I activate the captions. This should be M1. So M4. Of course, I need a train at the end. And I need a buffer. I changed the buffer here in the class library to a capacity of 4. And I place a buffer in front of each machine. The name, it's not interesting here. How's the name for the buffers? And also the train needs a buffer, so I can use one program to control all the machines and the train. Okay, I need 2 different controls. One control is I need to set the process time for each part, for each station here, depend on the part and the work plan of the part. And so I need one method. This should be the entrance control of the stations. And this is quite easy. I need to set the proc time of this station. And I find these proc times in my table work plans. First column, the name is my key for the row, and in the second column in the work plan, I find the process time, and I need one attribute for the operation number in my MU, and this I need to make. Okay, you can also use this as a formula in the field proc time in the stations, and I need to add here in the part one user-defined attribute P, and it should be an integer, and it starts with 0. Okay. This is the entrance control of station M1 to M4. You can hold down the shift key and then drag the method onto the stations, and so it becomes the entrance control of the stations. We need to activate before actions because we want to set the proc time, and this we need to do before the MU is entered the station completely. And so we need to activate before stations in all station. Activate before actions. Okay, this is the first step. So we get we get another proc time depend on the walk plan of the parts. And then you see it's not connected with connectors here. I don't use flow control to control this flow. I want to control this with the exit control of the station, and I need some method to select the next station based on the walk plans of the parts. And so I need another method. Move to next station. Also, it's only some lines. We need to increase the operation number of this of the part. It's at point OP. So we get the next station. And then I need only to read in the walk plan the first column of the operation of this part. So it's walk plans. Walk plans are in the first column again. At point name is the row. Then first column at point OP, I find the next station, and the buffer in front of the station is pred, the predecessor of the station. We need to wait until this next buffer is not full. And then we move to this buffer. So that's all for programming in this example today. And this is the exit control of all stations and of the source. So I just break it on source and M1, M2, M3, and M4. And then you have two controls. The first control sets the proc time, and the second control moves the part to the next step inside this job shop production system. Okay, and now one is missing, and now I need a sequence. For my source, I need a sequence cyclical. I don't generate it as batch. I have a sequence from single parts. Just move it to the source, and then it should change the setting and mu selection to a sequence cyclical. And this is what we need, what we want to optimize. And so we need to create a sequence. I track the part inside. Here it's 1. And here I set the name. It's A. I want to produce in this sequence 4 A's. And so I make 4 entries in this table for A. Next, I want to have 10B. So I copy this row and change this to B. And 2, 3, 4, 5, 6, 7, 8, 9, 10. Then I have 5C in this sequence. Again, I take this one, change this to C. Five and 3D. Okay, this sequence can be hundreds of lines from your production. I have done several such projects for electric coding, and there you have different recipes for each part, and you get some forecast, maybe 100 or 200 lines of products, and each product may have a different recipe, and now you can try to find an optimal order of tasks here. The base could look like this. You have 3 of them, 10 of them, and so on. Normally much longer. Yes. Now we need to check if our program is running. I close this and let it run. One important step is we need to limit the time here. So I set an end, maybe 10 hours. I don't have stochastic elements here in this small example model, and so I don't need a very extended simulation time. But to run the optimization, you need to limit the time here, otherwise it doesn't work. So I run this, and then I get a result, and it's 121, and this I write into my frame, and this is my starting point. Okay, with this sequence, I get 121 after 10 hours. And now I need to change this order. I need to change the order of this Perl chain in order to optimize, in order to increase the throughput. And you can imagine if this is hundreds of lines, it's really incredible high number of possibilities if you try to simulate all possible variants of this sequence. And here you can use the genetic algorithm. So first I need to add the genetic algorithm to my class library. So I go to Manage Class Library and add the GR wizard to my class library. Okay, then you can find it in user objects. Now in tools, here's the GR wizard. Okay, we need to make two settings. First, we need to set the result of the GR of this optimization, and the result is train.num_in. For instance, you can hold down the Shift key and drag train to the GA wizard. And okay, that's what's wrong. Just drag it without holding the Shift key. Now you need to select the attribute we want to have. Here it's .num_in or .num_out. Okay. And then take the sequence, hold down your Shift key and drag it to the GR wizard. Okay, and then you can open the GR wizard. You can find the optimization parameter here. If you open click, then you have here sequence of 22 elements. This is the parameter. And this is what we want to optimize. So we need to set an optimization direction. I want to have maximum output, and so I need to select maximum. And here you can set some, make some settings about how many generation you want to create for each one and how big should be a generation. We can let it here at 5 and 10 because our model is not so big. Configuration methods, you can add here a method that is called every time optimization run is running. We don't need this. Fitness calculation, you have two different ways. One is by table. If you open here the table, it's what I have tracked to the GR wizard inside here. It's .num_in. You can make much more complex fitness calculations. You can calculate this by method. Then each time one simulation run is finished, this method is be called and needs to deliver some value for as optimization calculation as a fitness value. A big topic if you have more complex optimizations. But in our very basic environment, this is already enough. Then click apply, and then I can reset my simulation and start the optimization. It took 0.4 seconds. Okay. In the tab Evaluate, you find the best individuals. Okay, it's the fitness value here my number of produced part is 128, and you have two different chromosomes, and the chromosomes contain the order based on the number in your original table, in your sequence table. At best, this first optimal chromosome is already set in your simulation. If I go here in my simulation, this is the chromosome here, and this is the row in my original table. Row 4, then 17, 12, 22, and so on. And this is the sequence, one of the optimal sequences with the result of 28 instead of 21. A, C, D, 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 B, B, and so on. And B was my critical task. And now I have two Ds, for instance, in parallel to the production of one B. And so we can create more than 21 in this sequence. Yes, here you can go back. If you want to make another optimization, you can create this the original order of this table using this origin column. You can sort this, and here you have the original order, and you can change this and make other optimizations. Okay, it's not rocket science to use this GA wizard for Perl chain optimizations. It may take time if the sequence is really big. Then you need a lot of simulation steps to find optimum, and you have some visualizations here. If you can show, you can see the evolution of the solutions to see, okay, it's going to be the best here. If you have here, if it stops immediately without any creating more generations here, then maybe it doesn't matter the order of tasks. And so this is the first requirement. If you want to optimize Perl chain, then you need something that is different between the different orders inside of this sequence. And this offspring diagram here, you can see all the values from the optimization. You see, okay, here are the two best individuals, and then it becomes weaker, and then it stops. Okay. Any questions?
There's a couple in the chat.
Yes. Okay. if you have more than one train, for example, can you add the values together for total parts into the train? Yes, you can do. You can do this here in this table. You can here the target value, you can write plus. And then if you have a second, okay, I need to create a second train first. So now I have train 1. Okay, I have to duplicate this. Open plus, and then okay, you can do this in this way. You can, yes, you can make really, you can make also more complex calculations here in this table, or have several values with different weightings that it's, and then it calculates from this one value to calculate the fitness value. And if you have a very, very complex fitness value calculation, then it's better to do this by a method. So a second one is there's a way to input simplex calculus into a plan simulation to assure that we achieved a global minimum maximum. I guess then you need to make your own calculation. Here with the genetic algorithm, you don't have the guarantee that it finds exactly the mathematic optimum or the minimum. It's yeah, maybe the steps are too big, or you don't have a guarantee to find this optimum here. And you cannot change this. I don't know. But I don't think there's no guarantee to find a real minimum maximum exactly. Is it possible to optimize a flexible job shop scheduling where each operation has a choice of more than one machine? It only runs experiments. What you do to select the machines, and it's your job. It only runs experiments, and if you select, it's to optimize the job shop scheduling. There are other programs better doing this job. If you want to optimize optimize the utilization of each machine. But Tony, yes, normally if you have a program that selects the next free machine, this is only changing the order of something here, the sequence. There are other optimizations possible here with the genetic algorithm, for instance, for allocation. And so you can make other optimizations also with this genetic algorithm in plan simulation. Could you please explain more about the by method option fitness calculation? It's you just assign a method and return a value, a real value from this method. It's not a big deal here. And inside of the method, you can do what you want. It may be a very complex calculation if you want to work with penalties that you can check, okay, if there is some attributes that you have set as a limit to something, and your one result is hurting this limit, then you can set penalties, and then you can create from your original results and the penalties one value to exclude such solutions from the optimization. You are free to do all. The only one you need to do is you need to result a value, and the value should be minimum, maximum should be connected to your optimization direction. What's the best way to define the number and size of generations? Please refer the literature. It depends really how complex is your model and how small the steps you need. If you have thousands of lines in a sequence, then maybe you need to be more. You need more generations or more steps, and it's also depend on if you have some stochastic elements in your simulation. We don't have anything here, and if you have some failures or some random distributions in your simulation, then you need to make another size of generation to get a stable statistical value. It's like in the experiment manager. And yes, it's a matter of testing. If you don't get the results you want to have. How you decide if you want to use the experiment manager or GR-Wizard. If the experiment manager says this will result in 100,000 experiments if you use the multi-stage experiment. So if you have this experiment manager and you use tools, multi-level experimental design, and the result of this design is hundreds of thousands of simulation runs, then maybe it's better to use the GR-Wizard to save time. And one optimization is allocation, where you allocate a value to a certain, for instance, the size of the buffer, and you want to make a simulation for 10 buffers and each buffer with 20 steps, and it will result to 20,000 of experiments. You can do all the experiments with the experiment manager, or you feed this into the GR-Wizard and you get the results much faster. Maybe not exactly the optimum, but you get results much faster. And so if it's almost impossible to make all the experiments with the experiments, then maybe it's the better choice. It's the better choice to use the GR-Wizard. And you find a lot of documentation in the help. And there you can also read what's behind the GR-Wizard. But you cannot change it. You can look behind this GR-Wizard. Oh, just hold down your Alt key and double click on the GR-Wizard. Oh, where's my method? What here? If you are interested about the backgrounds of this GR-Wizard, then hold down your Alt key and double click the GR-Wizard, and then you see all the programming and can have a look here into the programming of this GR-Wizard. Okay.
Right now on your screen, you should see a slide that's showing a URL for the Plant Simulation Virtual User Group. So this is the URL you can click on right now that will take you to the forums that are shown in the image there. And that is where we post the recordings and invitations to the session. So the registration links are posted there every 2 weeks. And the animation is showing you how we recommend that you follow the topic for this URL, and then click on the envelope icon to select every post for email notifications. So this will just send a system message as soon as we post the recording. That will send you a system message that says, that the video is up for that, and you can watch this recording, and all of the other recordings are also hosted at that URL. And similarly, when we say, post register now for the next topics, they're there. But since you're on this call right now, these are also clickable links. You'll see our next meeting is on Wednesday, September 17th at the same time. Stefan will do a session on worker crane synchronization. And then on October 1st, one of the product managers for Technomatics Plant Simulation is going to go over, I don't know whether to call it a plugin or a library. I think it uses both, but called Optimize My Plant. There's that for you. And this last slide, you can click there on Stefan's name. That will take you to his customer community profile inside of the forums. Once again, I will have the recording posted by the end of the day, Friday, Eastern Standard Time, East Coast in the US, at the link that is there on the screen. So we do have about 9 minutes left. If there are any other questions, this is definitely the time to raise your hand or throw it in the chat before we log off for today. If not, we can only assume that that was a very clear and detailed explanation, Stefan. Seems like folks, yeah, there's a thumbs up to that folks were able to get the information that they needed. Any last words, Stefan? Any requests from the audience?
Thank you. The next topic is the explanation about the Walker crane synchronization from my presentation in Amsterdam. If you're interested in the programming behind, then it's the right topic for this. And you need to download a file before the webinar. Okay.
Sounds good.
So thank you for your attendance, and until next time.
All right. Bye, everyone.
Goodbye.